Hi friends, welcome to follow up. Let's have a look at problem 2950, number of divisible substrings. In this video, we are going to provide two solutions based on the same strategy, that is partial sum, or some people term it as prefix sum. The first implementation will be a square term complexity solution, and the second one will be a linear term complexity solution. And also I want to point out the connection of this problem with a prototype problem. With that said, our plan will be the following. First, we are going to quickly digest the problem requirements, and then we do the algorithm analysis, and finally we share the codes. With that said, let's first digest the problem. So here we know the character of English alphabet has been mapped to a digit as following. So this is like our phone keyboard, right? So a string is divisible if the sum of the mapped values of its characters is divisible by its length. Given a string S, we want to return the number of divisible substrings of S. So that's the main statement. So from the main statement, we know this problem is a counting problem. But essentially, we are working with a numerical list, right? Because we can consider the corresponding mapped number list for the string. So here are three examples. Let's look at example 1. So it's a very detailed explanation, and the output is 6. Here is one point I want to point out, because each single character substring is divisible. The reason is that its length is 1. Every integer divided by 1 is divisible, right? So the constraints are the following. First, the length of this string word is bounded above by 2000. So if we have an n square term complete solution where n is the length of the word, it's bounded above by say 2000 square, which roughly 10 to the power 6, right? So this basically can pass all the test cases for leetcode problems. So this is one point to notice. And secondly, word consists only of lowercase English letters. So this is actually a consistency assumption, because here we are only giving the map information for those numbers, letters. So with that said, we are ready to look at the strategy and algorithm analysis. We are going to use partial sum and give two implementations. So the first one is a verbose one. We are going to check all the possible substrings, right? But we want to make sure. So when we look at the corresponding sum for each subarrays, so this sum computation is O1 in term complexity. The second one is we're going to use the dictionary and check trick again. So this will give us a linear term complexity solution. So our plan is the following. We are going to give both, but the first one is for the problem digest, but it can be very crucial when you practice coding, right? The second one is a little bit technical, and also we want to use something called decoupling in mathematics. So with that said, let's look at the coding. So the first one is verbose one. So we are going to use this check and for all the substrings by way of looking at the prefix sum or partial sums. Let's look at the coding. So first I want to map the characters to the digits. So this can be easily done, right? So we can get the A, B, C, D, E, F up to Z, right? This is the ASCII lowercase. And then I want to make a dictionary, right? So translate this graph into a dictionary. So this is super easy, right? So for I character in enumerate, let's see, ASCII lowercase. So here I start from 1, right? And then what we can do is that, so we can map the character to be, so the character divided by 3, so the integer division, because each group roughly has 3 characters, right? And then we add 1, right? So you can print out this D to check if it's right. So here AB is mapped to 1, and CDE is mapped to 2, and XYZ mapped to none, right? notice that the characters is mapped to characters between 1 and 9. This will be important for the second solution actually. So with this information available, let's quickly get the length of the word for convenience. And also I want to translate the word to be a numerical list. So this just a dictionary character for character in word. So this is the simple list comprehension. So now in order to retrieve a sum from index I to index j, so we can use partial sums. Let's see, partial sums. So in order to retrieve those quickly, I want to use a dictionary. So this is the use space treated for time. So here I'm going to do I is so x for I x in enumerate word. So here I is the index and x is the sum. So now in order to get the partial sum, what we are going to do, so for I in range starting from 1 ending at m, so what we are going to do is partial sums. So the current one, it will be incremented by partial sums from I minus 1, right? So here I start from 1, but you can actually also start from 0 if you like, or and I can do something like this, partial sums. So if it's -1, I'm going to set it to be 0. So this is just to treat the substrings starting from index 0 and ending at a certain index. You will see this point. So now let's see, we know that each single character substring is a divisible one. So I'm going to start with a result by n, right? This is length. And then we are going to consider substrings of length 2 up to length n. So this is easy for I in range, so n minus 1. Then for j in range, so because I want to consider length greater than or equal to 2, so I'm starting from I plus 1, then ending at m. So in other words, we are considering the substring starting from index I and ending at index j inclusive, right? And then the length, so let's write some detail, will be j minus I plus 1. And the sum will be nothing but partial sums. So starting from j, so we want to include this one, and then partial minus partial sums, so I minus 1, right? So since I can be 0, that's why I add a -1 here, right? Just to absorb all those cases. So basically it's a check. If s divided by length is 0, right? Or you see modulo this one, and modulo this one is 0, right? It's divisible. So once they have this one, we are going to increment this result by 1. And then we just need to return the result. So this forms a first solution. Actually, from this solution, basically you know the main logic for this problem. Let's first do a test. Partial sum is not defined. Let's see, partial sums. So S equals partial sums. Let's check. Yeah, it passes one example. Now let's look at the generic case. Yeah, it passes all the cases, but a little bit slow, right? You look at the time, but you can run more times to have a better feeling. So now let's make a first small comment. So here I start result from n, but if you write this 0, right? So then you start from here from I, then it means that j can be I. So in this case, we will include the substrings having length 1. So this is also right? So notice this subtle detail. Now you can do a check. Oh, it's not right. Let's see. For I, so here I will be from up to n, right? Yeah, it passes, and it will pass all the generic cases. So this is the first solution. So now I want to give another solution. So basically the second solution, but we need to explain a strategy called decoupling, right? So assume that we compute the partial sums according to the numerical list, and then at index I, so we get the sum, so up to index I and inclusive from its beginning. Let's say it's S of I, right? Then at later index will be SG, right? So I want to consider the substring from I plus 1 up to G, both inclusive. So notice that here I'm considering I plus 1. The reason I use I plus 1 is for convenience of computing the sum, because SG minus SI is the sum of the corresponding numerical list from I plus 1 up to G, right? Roughly speaking. So now the condition, so for this substring, say S or the word, so I plus 1 inclusive up to G, right? So this is divisible. It's equivalent to say SG minus SI, right? So this is the sum, and modulo this length. The length will be G minus I plus 1, then plus 1, right? So this is the end, this is the start. But overall, you compute it, it will be G minus I, right? So this equals 0. But, you know, because it's a modulo operation, it basically means that SG minus SI equals some constant times G minus I. So it's for M integer. But for this problem, we know SG is larger than or equal to SI. Actually, if G and I are different, so this M is larger, right? So so in this case, the M actually, because this is a length, so SG, this substring contains at most this this number of characters. So this because of the characters are mapped in between 1 and none. So M actually it can be 1, 2, up to none. So this is an important point to digest, right? So actually M has a range. So then once the M is fixed, so basically we can translate this this expression. Let's call this expression star. So star is nothing but so you can do this. SG minus M times G equals SI minus M times I, right? If you look at this case, so the left side contains only index G, and the right hand side contains only index I. So this we call it decoupled. The two indexes are decoupled, right? So then we just need to consider subarrays which have a constant quantity for this quantity. That is, consider the quantity Si minus M times I. So M can be 1, 2, up to none, right? So now let's make a connection with a prototype problem. So if you have practiced quite a lot, you may know that this is a typical question. So given a list of integers, we want to find the total number of subarrays with sum equal to a given target, right? But in this problem, we want to find subarrays with sum equal to this kind of quantity, right? So, or the difference of this quantity to be 0, right? So this is the same. So with that said, I hope that you have grasped the major idea. Now let's look at the coding. The coding actually is very straightforward if you digest the logic. So I'm going to change this one to be solution V1, and now let's look at this one. Again, when you do this this one, you have different ways to do this one. So now let's use this one. So here what we are using is decoupling, and the dictionary and the check trick, and also partial sums, right? Or prefix sum. So first, I'm going to map the characters into its digit. So this can be done. Let's see, character map. So here I want to provide another one. Let's see, character. So I can do I plus the ordinal number of this A, right? Then we're going to do this. So we are going to map this one to be I plus 4 over 3. So 3 is the group, basically, right? So for I in range 26. So again, you can print this out. Character map. It's the same as this D. You have AB mapped to 1 and CDE mapped to 2 and XYZ maps to none, right? So you can easily fix this, right? So with that done, let's also look at the dictionary. So we want to use dictionary and check. So dictionary, so let's see, we're going to use collections default dictionary. This saves some lines of code, right? So I'm going to initialize everything to be a collections default dictionary. So it's a counting, right? So here, basically, the default key will be the M. So because, we need to consider this case for each M. M is 1, 2, up to 9. So with this done, you can think of this collection contains 9 dictionaries inside. Each dictionary corresponding to M equals 1, M equals 2, up to 9. And then let's do this for M in range 1 to 9. So it's 9 plus 1, right? So in other words, 10. So then dict this M. So I want to use a 0, right? The 0, like here, the -1. It's just for convenience, right? So I'm going to set it to be 0, right? This is the prefix sum, and if it's starting from index 0, the 0th term, we regard it as nothing. Or if you like, you can use -1 equals 0, the same. So with that done, let's initialize two variables. Current is a running variable to be 0, and the answer or result. So this is a counting variable. So we are going to return this one, return its final state. And this is a running quantity for roughly this Si minus M times I, right? So now let's look at the for loop. For I character in enumerate word. So here I didn't use specifically use this one, but you just need to look up, right? So here in the first version, we just try to make it clear. So now we start from 1, right? And then for 1, the current will be incremented by, so the current character, right? The map, the corresponding digits. So this one is essentially playing the role of the list compression here, right? So, but the difference is that in the first version, we isolated this list, but here we just integrally used this. And then we are going to check for each M, for M in range 1 to 10, right? 9 plus 1. And then we check the answer, right? So if we see that, so dict M, right? So we want to count this one, current minus M times the current index, that is I, right? So if it's appeared, so k times this number of times corresponding to M, it means that we have starting from that index I plus 1, so that index, let's call it I naught, right? Some I naughts. It can be multiple, right? The number of count will be this number, right? From those I naught plus 1, ending at the current I. So those substrings corresponding are divisible, right? So we increment that. And then we're going to update the dictionary, right? So for M, so we're going to do the current minus M times I. So the count will be incremented by 1 after we check that. Then we are going to return this answer. So this is another solution, right? So if you analyze this time complexity, so basically this outer for loop, the inner for loop is a constant. In other words, we have an amplifying constant in O of n. So now let's first do a test for this. It's not right. Let's see, character collections. Let's see, we have dict m equals 0. So here it's not, let's see, it's not 0. It's not partial sum. It's counting, right? So here, dict m is a counter or counting dictionary, right? Count for the partial sum, and it's roughly partial sum, actually counting this kind of format. So this 0 appears once, right? So now let's check. Yeah, it passes one example. So now let's look at the generic case. Yeah, it passes all the cases, but if you look at the time complexity, it's much less, right, in the scale, right? So with that said, basically that's the second solution. So the first version is very easy to digest. The second one, I need some thoughts, but if you practice quite a lot leetcode, this is actually also straightforward. But if you want to look at the prototype of this problem, you can look at this one. Given a list of integers, you find the number of subarrays with sum equal to a given target. I've got the problem number in leetcode, but you can check this problem. So for this kind of problem, typically we can use the trick called dictionary and check, or sometimes we use set and check. So with that said, we are basically finishing this video. So if you are interested in practicing more problem, you can follow up us in our channel, and especially you can look at the corresponding playlist. So with that said, thank you.